All right, so let's see. What did I want to say? Oh, yes, the first time I ever lectured at OPLSS was 2011. And I remember being very like, wow. And it was a very, very all-star cast. Frank was there. Benjamin Pierce, all my, my idols. Like, so I remember being very like intimidated. But anyway, it's been wonderful to be at OPLSS all these years. All right, so let's start where we left off. So I've started by putting the definitions back up on the board. I really hope that they're visible in the back. I think the size is okay, but I'm kind of wondering, yeah, is the chalk like dark enough? Might not be. Move forward, everyone. That's the solution. All right. So what we were talking about yesterday is how to prove semantic type soundness for the simply typed lambda calculus. I have not put all the typing rules of simply typed lambda calculus back up on the board, but I've put down the definition of the logical relation that we're using. And we did a few cases of the proof, right? So what were we trying to prove? We were trying to prove, remember there was lemma A and lemma B that we needed to prove in service of showing that overall the theorem we wanted was type soundness. Oh, this is better chalk. Okay. Type soundness, where we're trying to say that if a term E has type tau, then it's going to be safe. Right? And safe means if you run E for however many steps and you get to some E prime, then it's either E prime is a value or you can always take another step. All right? And in order to prove type soundness, we basically said we're going to do this, prove type soundness using the semantic technique, which is to define that logical relation. And in order to get this theorem, then I said that we're going to have to prove two lemmas, A and B, right? A is the lemma that we end up calling the fundamental property of the logical relation. Well, actually, let me write that separately. A will be a corollary of the fundamental property. So what we want to prove is that if some term is syntactically well typed, then it is semantically well typed. Syntactically well typed, you can create derivations. Semantically well typed, it satisfies that definition, this definition up here. And then lemma B says that if some term is semantically well typed, in other words, you can read this as the term is in the logical relation, the term is a valid inhabitant of the logical relation, therefore it's well behaved like the type tau, then it is safe. So it will not get stuck, right? And we proved lemma B. I was talking about proving lemma A. We did a few cases, but how do we actually prove lemma A? We prove it by proving FP, this theorem that is a classic with any logical relation that you will work on. And basically the fundamental property says that if a term is syntactically well typed, then it is semantically well typed. Okay? Now, this just looks like a bunch of symbols. Oh, she changed a turnstile into a double turnstile, right? What's the big deal here? But think about the meaning attached to this, right? Here we are constructing syntactic typing derivations using the typing rules of our logic. That's what we have. It's a very, like with any logic, there's just a bunch of rules. That is all you're allowed to use in order to create certain conclusions, right? In this case, conclusions about whether or not a given program in a certain set of, given a certain set of assumptions about the types of variables, what is its type, right? But here what we're saying is we're talking about the behavior. I'm just sort of reiterating this from yesterday because I think that's like the biggest takeaway of these lectures in some sense. Here, even though I've hidden under this double turnstile symbol, I've hidden a lot of stuff. But what is that lot of stuff really talking about? Well, it's talking about behavior of terms, right? I'm going to read all of these just back to you really quickly before we dive in, because I want you to think about them just in English, right? Just in terms of the intuition. And the word behavior comes up a lot. So here's how I read this, right? What does this say? What does it mean for a term to be semantically well typed, given a context that it has type tau? Well, I'm saying that if you give me a bunch of inputs a bunch of values that I can substitute for all the variables in gamma, but you have to give me values that all behave like the types that gamma says they should have. There's that word behave again. All the inputs should behave according to the types that they're supposed to have, all right? then if I plug in those inputs into my program, I will get an expression that behaves like the type tau. Behaves all over the place. Okay? So then what does that mean? What does it mean for values that you give me to behave like these things? Well, for that, we look at the value relation. Values, only the values true and false can behave like values that are Booleans. And why is that? Why does that make sense? Well, because if I stick them into the conditional part of an if-then-else term, the right thing will happen. And if-then-else is the thing that will try to use these kinds of values, and then the right thing will happen. Right? If I threw a lambda in here, my if-then-else will break. If I say if lambda, then something, right? That just won't work. So I've ruled out that possibility. I am thinking about how these values of the type bool are going to be used in a context that's expecting a bool. Much more important to think about how something is used when it comes to function types. So what are values that behave like types, tau1 or tau2? Well, they're things that are waiting for an input. And how will I use them? I will use them by applying them. So that, how do I use them is built into how I build this definition. So a function, or a lambda, behaves like a tau1 or tau2 if you give me something that behaves like a tau1. I apply the function to that, and then when I run, I eventually get back something that behaves like a tau2. Okay? And all of this like behaves like stuff is kind of critical because, again, I'm imagining I have a lambda somewhere in my program. You come along, you give me a well-behaved tau1. Now that bigger program needs to give me something that behaves like a tau2 because maybe the tau2 is another function type, and the rest of the program is expecting something that behaves like that function type, right? So we're building little blocks, and we're thinking very hard about how they compose. Compositionality is a very, very big feature of these kinds of definitions, okay? So all of this intuition, when you start to do proofs for this stuff, you start to see how things fit or fail to fit, right? If you don't get the definitions right, they fail to fit. Okay, so, and then when does an expression behave like a tau, right? Well, when I run it, and again, here's the essence of the behaves like. When I run something, if I can't run anymore, if I can't take any more steps, then what I have behaves like a value of the appropriate type tau. This value that we're saying the expression has, right? And so here, behaves like is really about what happens when I run it. Okay, that's how behavior is being sort of determined. How do I use it? Any questions before? Yeah.
Can you just explain quickly where G fits on?
Where what?
G fits into this.
Oh, okay. Can I explain real quickly where G fits into all of this? Okay, so right here, I want to talk about running the expression E, right? Even at the very, very top level, I want to think about the behavior of E. But the problem is I can't directly talk about running this E the way I am in this definition without closing off all the free variables because they're going to stop me from running. Right? A perfectly valid program might be X applied to Y, but I can't even run it, right? So what do I need to do? The first thing I need to do is, this definition is really telling me how programs behave, but it's about closed programs. So I want to get my open program to be validly closed in a sense, right? I want to close off all of the free variables. By the way, someone asked me before this, like, open terms or open expressions are expressions with free variables. Closed terms are those which do not have any free variables. Right? Just terminology in case you weren't familiar. So what we're trying to do is we're saying, give me a bunch of inputs. They have to be well behaved. So what is this definition doing? It's just going through and saying for every single X that sits in the environment, I didn't write G of dot, which is the empty substitution. For every single variable that sits in the environment, give me a value that behaves like, so if the variable is supposed to have tau, then the value you give me to stick in for that variable better belong to the type tau, better behave like the type tau. Okay? So that's how G fits into it. And I'll point out one thing in just a minute because we're going to do the proof for the lambda case, which that G is going to become relevant. Yes?
I just want to check my intuition of G. So like for, maybe not for this language, but for a slightly more complex one, G could refer to like an infinitely large set then, right?
Well, you're constructing finite derivation, so you'll never have an infinite context. But yeah, you can have...
Well, I mean the possibility, the V's that it could draw from.
Oh, the V's that it could draw from. Yes, absolutely. There are any V's right, that are legitimate values of our language, yeah, according to our grammar, and that belong to the semantic sets, these V sets that we have defined. This is a very types as set, think of types as a set of values kind of interpretation, right? Think of types as sets of expressions more generally, right? Yeah. Yeah.
Does that then assume that your type system is expressive enough to encode all of the like actual requirements? Would make something behave correctly? Because I feel like there are languages in which, because the type system is insufficiently expressive, you can have something that is technically of the correct type, but would still cause your program to behave. Like if you don't have a nat type.
So what you're talking about is what happens when we add more types, right? I think you're sort of slightly alluding to a completeness issue with types. So yeah, you might not have a nat type. Let's say you only have ints, right? What does that mean? It means that you can still use your typing rules. In a sense, your type system is coarser grained, right? You don't have those further refinements of types. Yeah. One way to look at this is you can always throw in more refined types. You can throw in more types into any language and add the appropriate typing rules for it. And this whole technique is actually very nice because I can just give you one more V definition. Like I could give you, I haven't added ints to this language, but if we did, I would just tell you V of int is all numbers n. Syntactically, they have to be numbers n. And that's it, right? If I wanted to give you nat, I would say, oh yeah, I have a nat type. It's all n, such that n is greater than or equal to 0. I can have int and nat, and then your job is to go and add the appropriate typing rules for it and do the work of actually proving type soundness for the additional cases, or for the additional typing rules that you've added. Right? But back to your completeness kind of issue, if that's what, I don't know if it's right to call it that. You're basically saying why, can you kind of sort of repeat or?
Maybe another way to phrase the question is when you say, so this has to do with the choice of V's, right? It's you choose any such V such that V is in the relation.
Yeah.
And then the output guarantee, which is that
Here.
You have the resulting closed term is well behaved.
Yes.
That is with respect to the granularity of your type system, right? Or that's what I'm confused about.
I see. Okay. So you're. Yes. So the question is, this definition seems to be saying something that is with respect to the granularity of the type system, and I would phrase that as with respect to the syntax of types that the language has, right? Because this is type syntax, right? If I don't have the type nat, I'll never be able to write down a function type that takes something and gives me back a nat, for example. Does that sort of capture the concern?
Yeah.
Okay. And that's absolutely true. But I mean, at the end of the day, I want you to think of this this technique as something, you don't start with the logical relation. You start with, oh, here's a type system I want to define. It's completely your choice how refined a type system you want to define. When I wrote down the grammar of types yesterday, right, I started really, really poor. I just have this, right? I can add int, I can add nat, I can add dependent types, refinement types. We can write them like this. Any x of type t such that, you know, x has some sort of property. I'll just write it as px. You know, you can keep doing that. That is your choice to add more and more syntax, more and more refined types, more sophisticated types. And then you will end up, when you add, this is moving away, when you add more types, you will also add typing rules for those types, right? Typing rules that introduce something of that type and that eliminate or use something of that type. At that point, you need to show that your additional typing rules are sound, okay? That they are giving you, you know, if you end up type checking a program, then everything will be okay and the program will not get stuck. At the end of the day, that's what we're after. At that point, you'll come back here and you'll add some interpretations for the new types that you just threw into your language. You're the language designer. You're the type system designer. Once you design it, you have to prove that it's sound. Does that kind of make sense? That's the process. So you can keep using this technique for more and more types. In fact, I'm going to add recursive types today, but I just wanted to throw this one up there, right? This is a refinement type. For those of you who have seen any kind of refinement or dependent types, this just says you have this notion where any value or expression can be assigned a type of this form, which it basically says that that expression will evaluate to a value which will have, let's just do int as an example. That is an int, and then I have some predicate on that int. I could write down things like, oh, x is greater than 10. That is a valid refinement type. It won't be in the grammar. That's an example, right? But then you can actually give meanings to things like that. You just have to give the appropriate interpretations. The technique is fully general. You can keep growing it. Okay. Let me get rid of these, but I'll keep this line because I'll use it in a minute. All right, let's go back and do a proof. I think I'm just going to do this here. Okay, so these things don't stay up. All right. So we said that we were doing this proof of the fundamental property by induction on this typing derivation, and we did the cases for variables and true and false. I'd just like to do the case for lambda, and then I'm going to ask you to do the case for application as homework. Right? You don't really learn what the technique is about or how the definitions, which parts of the definitions matter unless you do some of these proofs. So you should do it. Okay. So, but we're going to do the case for lambda. Okay, so here is my lambda typing rule. And we... Okay, what we want to prove is that if the term is well typed, so we have this, right? We want to show that under gamma, double turnstile, right? Semantically, this lambda has that type. Okay, so that's what we want to show. I'll start here. Okay, so the definition says, the definition here, right? Write it. So show that lambda x colon tau 1 dot e has type, semantically has type tau 1 arrow tau 2, right? This is the overall statement we're interested in showing, this side, right? I'm just instantiating it to the case that I have. So what do I do? Well, the definition says you need to suppose that you have a substitution little gamma that belongs to G of this gamma, our environment, right? So an appropriate substitution with the right, with values that behave like the appropriate types. And then what we have to show, so given this, show this, we have to show that gamma applied to our term, which is lambda x colon tau 1 dot e, belongs to E of, is an expression that is well behaved at our type tau 1 arrow tau 2. Yeah? That's what we have to show. Okay. Now, I have a habit of putting underlines under shows just to keep ourselves sane. Okay, I want you to notice that this is a substitution, and I can push it in. So this substitution can just be pushed in. This expression is equivalent to lambda x colon tau 1 dot gamma e. So it is equivalent to, so I need to show this. I can instead show this. Okay, all I've done is push the substitution in. And now this is our proof obligation. Okay, so what do we do next? Well, in order to show that a lambda term is in this E relation at tau 1 arrow tau 2, let's look at what the E relation says. It says that if you run the term, this lambda term, and you get to an irreducible expression, then you have to show me that it belongs to the V relation at tau 1 arrow tau 2. Okay? All right. Well, it's already an irreducible expression. Therefore, it suffices to show that my lambda term, since it's already irreducible, is in the V relation at tau 1 arrow tau 2. Okay? So this is what we have to show now, and we'll be done with our proof. Okay, so how do we show this thing? Now we have to go look at the V relation for tau 1 arrow tau 2 in order to figure out what we need to do next to show that fact. Let's read it. It says, Okay, you want to show me that a lambda belongs to this V relation at tau 1 or tau 2. First, you have to suppose that someone gives you a value of the right argument type. So suppose that we have a V that belongs to this argument type. So it's a V that behaves like a tau 1. Okay? And given that, we have to show that if I plug this V, if I basically apply the lambda to that value, right, then and substitute it in for x. So if I have body of the lambda, gamma E, and I substitute V for x, right, because that's what I'm doing in that definition, E with V for x, this is my E, this is my V for x, then I have to show that I will get something that is of the appropriate, that behaves like the appropriate result type, tau 2. This is my result type, right? Yeah.
Are you assuming that x is not in the domain of tau?
Yes, okay, good point. So we in the type systems world have a habit that I did not make explicit yesterday. Whenever I write gamma, comma, x, colon, tau, all sorts of books will tell you that this is an assumption we make. We assume that this comma means disjointness, that whenever I write this in an environment, I'm assuming that x does not appear in the domain of gamma. So yes. Okay. If you read Benjamin Pierce's book, Types and Programming Languages, it says that somewhere in the beginning. Okay, yes, I've just been assuming that whenever I write. So here I'm getting it from this premise, right? I have this fact. And that's why I get to it. I look at that and I say, yes, of course, x does not appear in the domain of that gamma. So therefore, this does not have a substitution for this particular x. Okay, so now we have to show this. All right, what do we do next? Well, first let me just note one thing. Again, I'm just going to play with substitutions. This is a substitution that's giving me binding for, let's say, x1 through xn, and now I have an additional x, right? So one thing I could do is I could write this expression as, oh, yeah, you have that substitution, but now I have a substitution for x. So maybe I could just write it like this, right? I made it one big substitution that I can apply to E. In other words, this expression and this expression are equivalent. Here I'm just doing the substitution after. Here I'm saying, oh yeah, when you do the substitution of all the other things, just do it then, right? So it's just a little observation, a little syntactic observation about substitutions. But we'll use it in a minute. Okay, so now we need to show this fact. All right, so if we have to show something is in the E relation, what do we need to do? It says, all right, go ahead and run the term until you get to something irreducible. All right, so we're going to say, all right, suppose actually, I'm not going to do that because that's going to make things longer. Let's note that we have not used our premise yet. Yes, question?
Does this basically just follow from the hypothesis?
Yes, that's what I was about to say. I was like, why am I unwinding another definition? I don't need to. Yes, so we have not used our premise yet, right? Like the premise of the typing rule. In other words, but we can, and let's do it now, right? So because we have this fact, we know, right, by the induction hypothesis, we have, my board placement is not working. By the induction hypothesis, we have that under gamma colon x tau 1, from this, we know that we have this fact with a double turnstile here, basically by the induction hypothesis, right? Okay? So now we have this fact by the induction hypothesis. Let's use it. What does it mean to use it? Well, okay, let's look at the definition. It wants us to provide a substitution for all the things in gamma as well as the x. Okay? And then that substitution will need to belong to G of gamma comma x, right? So let's do it. We actually have something right there. That's the one we're going to use. So I'm going to say instantiate this thing, this definition basically, with this substitution, gamma with x maps to v. We need to show that this thing is in G of gamma comma x colon tau. Can we show that? I will do it verbally, okay? Yes, we can show that because we know that the little gamma, let's look at the definition of G up there. In order to show this is in G of gamma comma X colon tau, tau 1, ours is a tau 1, we need to show that the little gamma is in G of gamma, which we have already by assumption. I'm getting a little lost. Boards. Like, where'd my board go? Okay, we have this already, right? And now we also need to know that the V belongs to V of tau 1. And we have that already as well. So given those two facts, this is true. Okay? So since that is true, we can successfully instantiate this definition with our substitution, and we know that it belongs to the appropriate environment, the interpretation of the appropriate environment. Therefore, we get to conclude from our induction hypothesis that, let's go here. Therefore, so again, just from that statement, we know that our substitution applied to this particular expression belongs to tau 2, E of tau 2. Should I do this last part again? We have this by the induction hypothesis. We're going to use it. How do we use it? To use it, we need to provide it with a substitution that is in this environment. We figured out how to do that. We used our extended substitution and said, yes, it is in the environment that is listed over here. All right. Now, therefore, since we gave you a good substitution, this statement gives us back a fact. The fact is that the substitution we provided, gamma with X maps to V, applied to the program of interest, which in our case is this E, right, belongs to the type that we care about, tau 2. Therefore, we have that fact. Guess what we needed to show? Exactly that fact. This is the last show statement on the board. Okay? So we have just proved it. I want to say one thing, so maybe I can delay the question just 1 second. Oh, yeah. Go ahead. Yeah.
Just so I understand everything we've just seen in the last 5 minutes.
Mm-hmm.
I didn't really check last lecture. So basically, what we were trying to do is show that any syntactically well-typed term continues to be valid no matter what the context is. That's more or less what developers are.
I don't know how to interpret continues to be valid.
In the sense that if you apply it under any context, any
Yeah.
arbitrary context,
Yeah.
evaluate it fully, the result will be guaranteed to be a value of the type that you want.
Yes, that is correct. The word context, the way you're using it here, is any substitution of values for the free variable.
Yeah, it's
Yes.
the gamma.
It's the gammas. Exactly. Yep. Yep. Exactly.
And where we're showing this particular case, which is the way we're trying to show this particular case is assuming that your lambda expression E obeys this property,
Mm-hmm.
then to show that the expression lambda x dot E obeys it,
Yeah.
you just pretend that you call that function with x.
Because that's what the definition says, right? The V relation for tau 1 arrow tau 2, right? That V interpretation, the value interpretation, says if you want to show me that a lambda behaves like this type, you have to apply it.
Yes.
Yes.
That substitution literally is a new context for that E.
Exactly.
You apply it,
Yes.
and that's exactly the point.
All right, let me just repeat that last phrase because that's exactly the point I wanted to make when I said, can I delay the question?
Oh, I'm sorry.
No, that's perfect, actually. Perfectly timed. Sorry, what's your name?
Rohan.
Sorry?
Rohan.
Rohan? Okay, so what Rohan just pointed out is that we did this interesting thing with the argument to the function, right? We took the argument to the function, we added it to the environment here, right? That led us to a place where basically we ended up saying this, so, okay, let me put it a little differently. I'll step back. Lambdas are one of the most interesting cases for logical relations, and I've been saying this since yesterday, and I'm going to point out a very, very interesting fact here, which is lambdas are about, when you use a lambda, you are working with an input that you don't yet have in your program. It will come from the outside, okay? And if you look up here, right, when is a lambda well typed? It says, oh, okay, when I make an assumption about its input, and then the body behaves like the right type. All right. But what we've basically done is there is this parallel between what the semantics of function types is saying, right, what the interpretation of function types is saying. It's saying, if you want to show me that this lambda behaves like a tau1 or a tau2, you first have to give me a tau1. And if I run, I will give you back a tau2. Look at what's happening at the top level definition right here. Basically what happens at the top level definition where you plug in things for free variables will always kind of line up with what's happening in the lambda, just in a more general sense. This is basically allowing you to handle a multi-argument lambda. It's saying, if you give me a whole bunch of inputs, then you can think of this as the body of the function. I'll get to run, and I will give you back a tau2. These two are like tightly connected. If they don't connect properly, you won't be able to do your proofs, right? Okay, so the top level definition is about open terms. And it's saying, if you give me the inputs that behave well, that behave according to the types they're supposed to have, then I will give you something that behaves like the result type. Yeah?
By multi-argument lambdas, this also works for nested, right? Or are those basically the same thing?
It would be fine for nested. Yeah, same thing. Okay. All right. I should move on. All right. I would like you to do the application case on your own. The application case is, basically where you have the app rule E1 applied to E2 has some type tau, put in the premise, right? Just do that rule by the induction hypothesis. You will have, you'll get to use the induction hypothesis twice because you have two terms at the top, right? You have a typing derivation for E1, you have a typing derivation for E2, so there will be two induction hypotheses. With the application rule, it's a question of staging. You have to look at the operational semantics and say, oh, the operational semantics. First, I run E1 down to a value, and you'll get some fact like, by using your induction hypothesis, you'll get to conclude that eventually this E1 is getting to a value that belongs to tau1 or tau2, okay? So it's in the V relation of tau1 or tau2. Then you'll run this down. You'll get a V2 that by this induction hypothesis, sorry, I'm not putting in gammas, but I should. By this induction hypothesis belongs to V of tau1. And then you'll get to use the definition of V of tau1 or tau2 to continue the proof and complete it. All right? So there's a very kind of, what do I run first? Oh, I got a value. All right, it belongs to this interpretation. I know this from my first induction hypothesis. Oh, now what do? I run the argument. Now I got another value. Oh, it belongs to this interpretation by my second induction hypothesis. And now something interesting happens. I have something in a V of tau1 or tau2. I have something else in a V of tau1. That tau1 could be arbitrary, but the V of tau1 or tau2 is an actual concrete definition that you can unfold and say, okay, so what should happen next? All right, and that lets you complete the proof when you unwind that definition. But do it tonight, just the mechanics of it are fun and interesting to see how they line up. Yes?
I had a question on the other board. It's one of the ones underneath there. But,
yeah.
So we said that, it was the next one, sorry.
The next one, bottom one.
So, yeah, like this equivalence here next to show. I just wanted to double check that there aren't any issues with shadowing of X. Because, yeah, so I was wondering if you could comment on that.
Yes, I mean, basically, I have assumed. Oh, the question is, yeah, okay. Right, yeah, I know. Sorry, I keep forgetting. And sometimes they're so long, they're hard to read. They turn into a discussion. Okay, so is there an issue with shadowing of X? So the concern is I quickly rewrote this substitution into this shape, and I asserted that it was okay. Is it actually okay, or is there could something go wrong in terms of shadowing of variables or something? Everything is okay because of my assumption, not assumption, because I know that X does not appear in the domain of big gamma. Therefore, I know that X does not appear in the domain of little gamma, right? So, because the domain of big gamma and little gamma are the same, top of the board, right? Okay, so because of that, basically what this substitution is doing is it's doing for every single variable, it's just going in and doing a pointwise substitution. We are not allowing any shadowing. We're assuming that every variable in gamma, right, just completely separate. You can do pointwise. You can do the substitutions in any order whatsoever. Those properties are what makes it okay. Right? So whether I do it before or after, this expression will still have a free x if the original expression E had a free x, right? And then we're doing the substitution. But it's perfectly okay to do any of these substitutions in any order because no shadowing is happening, right? So it's fine to just pull it out. Yes?
Does this assume that V itself is closed? Like if V
The values are all closed. Exactly. So that's a very important point. When we built those V relations at the top, they are sets of closed values. The E relation, sets of closed terms. The only place where we start to talk about open things is at this definition, which I'm referring to sort of as the top level one, right? This is for open terms, and gamma tells us exactly what free variables are free that are making it open. Okay. All right. So far we have a terminating language, right? Let's make it non-terminating. All right, I'd like to go and pretty seriously enrich my type system. Where did I'm going to add, so this is my simply typed lambda calculus with just booleans and functions, but I'm going to add recursive types to it. So how many people are familiar with recursive types? Okay, a lot. All right. I'll do a quick thing. Let's go back to the example that someone threw at me yesterday when non-termination came up. They said, what about omega, right? Omega in the untyped lambda calculus is this term, lambda xxx applied to lambda xxx. And I talked about how when you run this, it's just going to loop forever, right? It just steps to itself, so it loops forever. We cannot type check this in the simply typed lambda calculus. So I'd like to now add recursive types to my language so that I can type check this term. Okay, so we will have a much stronger language. It will be Turing complete. It will have non-terminating programs. But more generally, let's just quickly talk about recursive types. What are they? So in languages like ML and Java, most languages have some way of creating recursive types. They let you do things like create types for lists and trees and streams and so on, right? So let's talk about a simple example. Suppose I want to define a type like tree in ML, okay? Basically, a tree can have a leaf, or I'm just going to do trees which have nodes that can store integers. So I can have a node of int cross tree, right? In a sort of Java-like language, I could do something like class tree, and then say, I have an int value in the node, and then tree left, right. Right? That's like sort of the syntax roughly for it in, ML-like languages, Java-like languages. But basically, we can't define this kind of tree type. Or I could do a similar thing with lists, I could say int list needs to be either nil or cons of an int and more list, right? How do you define these kinds of things? So let me write this a little bit more abstractly. I'm going to give myself one more type actually over here. A very basic type if you haven't seen it. I'll put it here. The type unit, often written as 1, sometimes written as UNIT, But basically, the unit type is something that has only one inhabitant, which we just write as a sort of an empty tuple usually. That is the only value that inhabits the unit type. You can't really do anything with it. But it's very useful for representing something like, the leaf of a tree or the nil in a list. Okay, so I'm going to rewrite my ML tree type in a slightly more succinct fashion. So basically what we're after here in more SPLC-like syntax is a type like unit. Oh, do you guys know about sum types? I'm realizing Paul has not gone before me. Uh, Frank talked about sums? Good.
So you need this stuff as well.
Okay, all right, great. Oh, units, all right, of course. Okay, so I'm going to say that my tree is either unit for the leaf case, or it is a tuple with representing the node, int cross tree cross tree. Okay, so what do I do if I want, how do I construct a type like that in, if I wanted to extend simply type lambda calculus with something so that I could actually represent these? Morally speaking, what this is it's kind of like, I'm trying to define a type, but then I'm using the type itself in the definition, right? That's the problem. So we can, basically what the tree type represents is many, many different views in a sense, right? This thing, if I sort of call tree an alpha for a second, just an abstract name, it is equivalent to unit plus int cross alpha, but then it's also equivalent to unit plus int cross, inline the whole thing, right? Unit plus int cross alpha for the first tree, and then do it again, unit plus int cross alpha for the second tree. I mean, you can just keep substituting for that alpha, right? Now I can take this bigger one and substitute it in for these particular alphas, right? Because that one type is representative of all of these different views, right? So what we really, so how do we think about these things? How do we think about like sort of this infinite process, right? Basically, we need to think about fixed points, because we're trying to take the fixed point of some sort of function that is building a tree type for you, right? So I'm going to say, so let's compute the fixed point of this process. Writing is too big. Okay, so I'm going to give myself a function, f, and then we're going to find the fixed point of f, okay? So f is a function that takes some type alpha. This is the type I'm trying to build. It's the tree I'm trying to build, okay? But it's saying, give me a type alpha, and I will construct a type tree for you. And it gives us back unit plus int cross alpha. Okay, this is my tree builder function, if you will. Right? What I need in order to get the actual tree type is the fixed point of this function. What is the fixed point of a, so if we, what is the definition of a fixed point? If t is the fixed point of a function, definition of a fixed point is that if t is the fixed point of a function f, if t is equal to f of t. Okay, that's the standard definition of fixed point. T is the fixed point of a function f if t is equal to f of t. All right, so let's see how we use this for our purposes. What I'm going to do, in my simply typed lambda calculus, I am going to posit the existence of a fixed point builder, something that builds a fixed point of these functions, a fixed point type constructor. I'm going to call it mu alpha tau, right? So if mu is this thing that can take an alpha and give me back, and if given a function like f, if mu is a fixed point constructor, then this fact has to be true. Let me just write it down and then we'll read it. Okay, this is a fixed point constructor. I'm positing its existence. That means because it is a fixed point constructor, right, that means it has to be equal to f of the fixed point. That's all I've written down so far. Mu alpha of f alpha has to be equal to f of mu alpha of f alpha. All right? Okay. Now let's just play a little bit of a syntactic game because I don't like all these f alphas sitting everywhere. So I'm going to start writing this little f alpha as a tau. Put a tau over there. What that means, of course, is that tau has an alpha free in it. Yeah? Okay, because it's stand-in for my f alpha. Okay, so what have I just done? I've just given myself a slightly shorter way of writing the following thing. Yeah? Haven't done anything terribly exciting yet. But now let me note that tau is f of alpha. So maybe I can get rid of this f, right? Basically, I can say that what's happening here is I'm taking mu alpha tau and substituting it for all the alphas that appear in my function f. Yeah? Okay. So that basically means that this is equal to tau, tau is the body of the function f, right? To tau with mu alpha tau for alpha. Good? In other words, mu alpha tau is equal to tau with mu alpha tau for alpha. All right? What I've just written on the board, if we skip the thing in the middle, is basically something that we can, if we add, I posited the existence of a recursive type constructor, mu alpha tau. If I add that recursive type constructor to my grammar of types, I'll give myself alphas and I'll give myself the recursive type constructor, mu alpha tau, okay? Then basically what the most interesting thing about these recursive types is that they let you fold the view into the recursive type, the collapsed type, the original tree, or they let you expand the view and say, oh, you know, the tree actually, it's either a leaf, the unit case, or it's this tuple with an int and paired with 2 more alphas. And then we can go expand the 2 more alphas as well, because recursive types give us the ability to keep unfolding the view as we need to. So where am I going with this? Basically, this is the recursive type. It represents the collapsed tree. Okay? I'll show you how to write down tree using this notation in a second. But we can unfold this view to get the expanded view, which shows us, oh, really underneath it, it's this or this, right? Or we can go from this expanded view back to the original view of the tree. Okay? And this is normally, this direction is called unfold, because you're unfolding the view and expanding it. And this direction is called fold. All right? Now let me turn that into actual syntax and typing rules. But let's do tree first. How can we write down tree? If I have this recursive type constructor mu alpha tau in my language, basically my tree type can be defined in this way. As the recursive type, we want a fixed point of this. Mu alpha, which is either going to be a unit or it's going to be int cross alpha. This is how we define a tree type. We can also do something like int list. Let's do int list. So normally for an int list, we'd want something like, okay, it's either nil or it's cons of an int and rest of int list, right, in an ML-ish kind of notation. Well, let's turn it into something slightly different. Nil is represented by unit. So an int list can either be unit or, here's a sum type, it can be a pair of the int paired with more int list, right? But I'm using int list both on both sides. So now let's do it properly. Let's turn it into a recursive type. I'm going to say, build a recursive type. Think of alpha as that eventual recursive type. It was either a unit or it is int cross more of the type that I am trying to build. Okay? So once we have recursive types in the language, that is how we represent trees and int lists. Yes?
Does mu alpha bind alpha, or is alpha always true?
Mu alpha binds alpha, exactly. Because I got here by talking about that function, right? So I want you to think of that alpha double colon type that I wrote at the very top as the thing that the mu is binding. So whenever we write this, this is a binder. Alpha can then appear free in this body under the binder. Yes?
I seem to be saying that the fixed point is unique. Why is it unique?
Sorry?
You seem to be saying that the fixed point is unique.
It's the least fixed point.
But like, there's uniqueness.
Oh, the question is about, I seem to be saying that the fixed point is unique. Yeah. And this is positing the existence of a least fixed point. Okay. Let's actually give ourselves, so this is, just examples of how we can build types like these if we, once we have recursive types in the language, but let's go And oh, okay. Let's come back to this and actually give ourselves, for now I've extended my language, the syntax of types in my language with recursive types, but let's talk about what expressions we need to add to our language, and then I'll talk about values and so on. Okay, so once we have recursive types, we have all the other expressions that we had yesterday, okay? So Booleans, true, false, if then else, lambdas, variables, application. I am only going to add constructs for this, okay? So the new constructs that we want are going to be fold and unfold expressions. They are going to be the view shifters that I was talking about. All right, so I want an expression fold E that, intuitively speaking, takes any expression E that maybe that had this type and gives me back something that I can treat as something of this type. And I'm going to give myself an expression unfold E that takes something of this type and unfolds the view and lets me treat it as this type. Okay? So I'm going to add typing rules for these things that do exactly what I just said by pointing. How do we type check fold E? Well, let's do unfold first. How do we type check unfold of E? Well, unfold takes us from here to here. So if E is something of recursive type mu alpha tau, where again tau can be some expression, some arbitrary type expression that has an alpha free in it, right? We built a couple. Then unfold E has the expanded type, this one, tau, with mu alpha tau substituted for alpha. Okay? Here we do the opposite. If E has the expanded, type, so to speak, the unfolded type, tau with mu alpha tau for alpha, then fold of E has the type mu alpha tau. Now, one tiny little technicality that I should add. Normally, when we add this syntax, we will have to, if we want, type checking decidedly, you can't just look at an expression and figure out what the tau is and where the mu alpha taus are. So you need to, you need to annotate this with mu alpha tau to guide your type checker. It's not terribly important for the things that we're going to do for semantic type soundness, but technically speaking, you need that. Okay. When did we start? And when will we end? How much more time do I have?
I think you can, we have still 20, 30 minutes, I would say.
Okay, all right, because
Because we started 20 minutes later.
I see. All right. So then let's do the following exercise. Omega. Let's go figure out a type for omega. Now that we have recursive types in our language, we can actually type check omega. Okay? Let's do it here. All right, you guys are going to help me play code detective, so to speak, and we're going to figure out a type for this. All right, so basically we want to be able to write down a type right there, an annotation, right? Because in simply typed lambda calculus, our variables, our inputs are annotated, but we don't know what to put there. Why couldn't we figure out when we were just in STLC, why couldn't we figure out what to put there? Well, because forget about recursive types for a second, right? What type can we possibly put there? Well, we could say, okay, this guy is a tau. That means this guy takes a tau, and it can be some sort of tau or tau prime, but now you have two candidates. Which one do I put there? There's no clear answer, right? It's impossible. You can think about it for a while, but it's not possible. So what can we do with recursive types? Let's focus on just this guy first, right? Basically, what can we do? We have an X here. Yeah? Maybe I can treat this x as some sort of an alpha? Maybe? But then this would have to take an alpha and give me what? I don't know, give me something, some arbitrary type tau. But maybe we can work with this, right? If we could say, just like with the trees, at the end of the day, we wrote, you know, mu alpha tau. Did I erase it? At the end of the day, that alpha represents the whole tree, but here I have more alphas in it, so to speak, right? I can do it right here. This tree is really an alpha, and there are more alphas here. But then when we write it using a recursive type, we just stick in a binder in the front. Okay, because that binder is the place, you know, that's the shape that we can fold into the expanded view or unfold back into the collapsed view. Okay, so what if we treat this as some sort of collapse type, right? So this alpha that it's getting as input, can we treat that as can we do something like mu alpha arrow tau? Probably? Let's expand this out. What would happen? This is a mu alpha arrow tau. What is this? Is it an alpha? Yeah, right. Okay. So if this suppose that this guy is a mu alpha arrow tau. Okay? That means this guy wants to take that as an input. Let me put a fold here. Okay? So then we could do something like actually, let's just write it out. Can you help me make sense of that? Can we put a fold or an unfold somewhere to make that work? If x is a mu alpha arrow tau, then this is that type, right? Okay. What if this is the unfolded type? What would the unfold of this type be?
Alpha, or alpha to sorry, mu alpha over tau.
It would be, unfolded type would be, stick in mu alpha arrow tau right there, right? And then it would be arrow tau. What just happened? Let's type check this in our heads. Does it type check? I'm assuming that x is a recursive type, mu alpha arrow tau. This guy, right? Okay. Unfold of x takes a mu alpha arrow tau. That's good, right? Because it's an application. So it takes the thing, this thing has this type, we're good, and it gives back a tau. That means the whole application gives back a tau. So what's the type of the overall lambda? It is mu alpha arrow tau. This looks like success. Yes? Okay. Let's note it. Let's note it in our big expression. We should just call this self-application. Okay, here's self-application and its type. Right? But we still need to type check omega. We can, I'm going to say that we have only managed to type check the two terms. So this thing appearing twice in the term will type check. If you assume that X has this type, and you put an unfold outside the first X, then this self-application term, it's type checking. Its overall type of the self-application term is mu alpha, alpha arrow tau, arrow tau. Notice I picked an arbitrary tau. Because you're looping forever, then therefore it doesn't matter. You can pick whatever you like. It's never going to return. Any tau is okay. All right? Okay, so that's just an aside, but now let's go back. This self-application has this type. This self-application has this type. Clearly, that's not going to line up, right? But if this self-application wants a mu alpha, alpha arrow tau, this one does, right? How do we get this guy that has this expanded view to turn into this thing? Fold it. What does folding this type do? Makes it mu alpha, alpha arrow tau. So now you have a mu alpha arrow tau being provided to something that wants a mu alpha, alpha arrow tau, and gives you back a tau at the very end of the day. It works, but it is kind of interesting. So using recursive types, and another thing to note is that the type that we came up with for the X, you know, this is a very, type checking omega is very interesting. We are using our recursive type in the negative position of the function. It's kind of key to making this work, right? So yeah. Now that we have recursive types in the language, we are able to type check omega, non-terminating programs. We can do lots of other shapes of non-terminating programs as well. But this is sort of the classic example. All right. So I still have time. So here's what we're going to do. Now that I have added recursive types, fold and unfold, to my language, I still haven't told you how we run these things, right? We didn't talk about the operational semantics. Remember yesterday I said there are 3 pieces to a language. You first define the syntax, then you define the typing rules and the operational semantics. So we've talked about the typing rules that we need to add, but we have not talked about how these fold and unfold expressions run. So in the interest of completeness, I need to give you that. And then what we're going to do right after that is we're going to say, OK, the new typing rules that we added to our language, we want to prove semantic type soundness for this new extended language, which now has recursive types. So how are we going to go and change our definitions or add to our definitions of these V relations and E relations in order to do that? So let's get to it. All right. So first of all, operational semantics-wise. Remember, we had value forms. The value forms here will be fold of V. That's the only new. So we have all the value forms from yesterday, the lambdas, the true, and the false. But we will now also have fold V will be a value. Unfold V will not be a value. We want that to actually do something, and I'll show you in a second. Our evaluation context, what we will add is fold. So anytime you have a fold E, you always want to evaluate that expression E until you get it down to a value, right? Because fold V is the value form. So first I'm going to add an evaluation context that says that. It says, if you have an expression here, evaluate it down to a value. And then I will go ahead and talk about the reduction rule. So basically, the most interesting reduction rule that we have is that if you do an unfold of a fold V, the fold and the unfold cancel out, so to speak. You end up with a V. Because the fold and unfold are really just view shifters, right? So if I folded something and pretended that its type was, a collapse type, unfold kind of gets it back to that. Okay, so unfold, fold of V is basically, our one interesting reduction rule. All right, so that's just mechanics. Let's go do the interesting bit. No. I'm erasing that, and we're going to add recursive types. question is, how are we going to define that? All right, so before I try to define that, let me say a couple of things just as recap. So remember yesterday, we had all of these typing rules. We're trying to prove semantic type soundness yesterday and today. For every single type in our language, we said, what are the values that behave like that type? What are the values that behave like the type mu alpha tau? My typing rules ran away. What has type mu alpha tau? What shape? Not a lambda. A fold. And since I'm asking you for a value, it has to be a fold V, not a fold E. Right? Okay. So that's step one. So when does any particular fold V, who knows what V is, behave like a particular mu alpha tau? What did we do for lambdas? We said a lambda behaves like a tau on our tau 2 if when you use it the way that you use lambdas, which means by applying it, it does the right thing. How do we use a fold V? Yeah, I mean, if I give you a fold, a value of recursive type, so this is the introduction form, right? Introduction forms are things that produce values of the type of interest. Elimination forms are the typing rules, which are the constructs that are allowing you to use a value of that type and do something with it. So this is the introduction form. It introduces values of type mu alpha tau. This is the elimination form. It uses values of type mu alpha tau. Okay? So we have to think about how we use a fold V in our minds. It better have this type mu alpha tau, but we're just talking about behavior, not about the syntactic type. And we want to say that when I use this, what happens? So the only way to use a fold value is to unfold it. So more intuitively speaking, here's what I want. If I unfold this particular thing, then I should get some sort of expression. If I unfold it, I should get some sort of expression that behaves like this thing. Okay? So I need something that behaves well according to the type tau with mu alpha tau for alpha. That's what I need. Then everything would be good. I can make one observation. You notice when I did lambdas, I said, oh, give me an input, and then I went ahead and plugged the value into the body of the lambda. But I could have just as well have written that, completely equivalent yesterday, to have written that as the actual lambda x colon tau 1 dot E applied to the V. Notice that this in one step will step to the thing that I just erased, right? So they're completely equivalent to write it that way. I'm in the habit. Frank asked me about this after my lecture, but I've been in the habit for a while for writing this, so I write it like that, but you can totally write it the other way. The function applied to the input. Okay. Now, I showed you that because I'm basically doing the same thing here. Unfold of a fold steps to what? V. So we can totally write this as V belongs to E, that. But furthermore, now that it is a value, we can change that. It's a value. Okay? So just tiny little simplifications. But the tiny little simplifications really don't matter because there's something else wrong. Sorry? You're sort of defining it in terms of self, exactly. The story of recursive types, right? They're always just like circular. All right, what is happening? The logical relations that I defined yesterday, I actually didn't take the time to point it out, but they were defined by induction on the types. Okay? The V relation for bool does not use any V relation. This is the base case. It's well-founded. It's all good. The value relation, when I tried to give an interpretation for tau 1 over tau 2, inside it, it uses V of tau 1, which is a smaller type than tau 1 over tau 2, still well-founded, and it uses E of tau 2. Tau 2 is a smaller type, but let's just go look at E to make sure that everything is still okay. Well, E of tau uses V of tau. So effectively, this definition uses V of tau 1, and then if we inline this, uses V of tau 2. Both of them smaller types than the type that we are trying to give semantics for. So everything was well-founded. Still is if I just focus on those two. Here, bad things are happening. I'm trying to explain to you the meaning of mu alpha tau, but inside I am using V of tau with mu alpha tau for alpha, which easily will be a bigger type. Easily you can construct many bigger types, right? So this is no longer a well-founded logical relation. And here's where I want to tell you a little story. I don't know how many of you have heard of this book Benjamin Shears edited. It's called Advanced Types and Programming Languages. ATAPL is how we refer to it. I think it's ATT. Anyway, so it's an edited volume. In it, there's a chapter by Andrew Pitts, and it talks about logical relations. The very, very last exercise in that chapter, so the exercises in that book are usually marked with like some sort of stars, not quite like that, but like stars, indicating the difficulty of the exercise. This last exercise is about, hey, all the stuff that we showed you in this chapter, we didn't do any recursive types. This last exercise says, how would you scale it to recursive types? By the way, this is an open problem. There are an infinite number of stars next to it. I think there's a star ... if memory serves me right. So this was an open, what I'm showing you now was an open problem for many, many years. Basically into the early 2000s. We did not know how to do, or right around 2000, we did not know how to handle recursive types, how to take a logical relation like this, beautiful structure, great proofs, everything's simple. For years and years, logical relations have been around for a very long time. Okay, knowing how to do proofs of SDLC, even if we didn't write it using this kind of notation back in the 80s or whatever, we knew how to do these proofs and people did them. You can add pairs to this language, you can add sums to this language, but things die when you reach certain circular kinds of types. Okay, recursive types were an open problem. Another really evil open problem, which I'll show you tomorrow, is mutable references. When you have an ML-like language and you can create new reference cells, allocate new memory, and then you can store functions in that memory, you can create cycles in the heap. Those cycles in the heap, very difficult to do logical relations when you have those kinds of cycles. That's another form of cycles. This is also a form of cycles. There are different forms of cycles. So basically what I'm going to show you now is a technique called step indexing. It's a way of defining a metric to ensure that these relations are well-founded. And it has been surprisingly valuable because it just seems to handle all sorts of circularities that emerge due to advanced type features. The two that I mentioned, recursive types, mutable references. But a few years after we came up with this, people realized, oh, you can even handle it, use it to handle things in concurrent languages, like where you have sort of locks, these circular kinds of things happening in the store. So it really works very, very well for a very wide variety of things. So let me try to show you the basic intuition before we have to stop, and then we'll continue tomorrow. What do we need to do? Okay. I want to basically think, what I want to do, so we're moving on to step index logical relations, which if I had space, I would write it somewhere. Step indexed. All right, and here's the basic idea. I am going to, instead of just defining relations, v tau, and saying these contain some values if blah, 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 I'm going to add a natural number to this index, to this relation. Okay, so all of these relations are now going to be indexed with what we call a step index. It's a number 0 or higher. All right. The intuition is the following. When I do my definitions, I am always going to be sensitive to the following sentence. I want to put a v in this set if the value belongs to the interpretation of tau for k steps as I run the program. Or a different way of saying it, if I were to run my program for only k steps, no more, I will not be able to tell that v does not actually behave like a tau. But if I ran it for more than k steps, then maybe I could tell that it does not behave like a type tau. But I'm not going to care. Okay? And this is going to let me define define well-founded relations. Because basically what I'm trying to do is I'm trying to use, until now my relations were defined by induction on the structure of types. Now I'm doing outer induction on this step count, the step index, and inner induction on a nested induction, I should say, on the type. Okay? So this is going to dominate, and you'll see what I mean by that in just a minute as we do this. But yeah, keep in mind the basic intuition. If you If you use it in a context for fewer than k steps, you cannot tell that v does not behave like a tau. But if you were to use it for more, it might not actually be a tau. Yes.
Is it similar to the concept of gas, or is it just separate?
I know that people have started using gas, and I think it's often people think that these two notions are related, but technically speaking, they're not exactly the same thing. They look related because they're both sort of talking about step counts, but in two different domains entirely. Yeah. Yeah.
If you were to try to write a real program simply typing in tableaux with recursive types, then would you require the maximum k to be the maximum depth of any recursive type that you use?
No. Okay, the question is, if I were to write an STLC program, STLC plus recursive types program, would I require that my types have a maximum depth? Like, are these, what your question suggests to me that you're thinking of the step count as kind of a syntactic depth. And what I want to
What I meant is that, like, if you were to try to evaluate it, you would require that your evaluation matches the
No.
depth.
The gas concept, I think, does that. But this won't. Yeah, you'll see. Okay, but let's start with just my assertion as to like what it means for vk tau. So I'm just going to start putting k's. I want to now say, do true and false behave like a Boolean for k steps? Do I need to say anything about how many steps? 0 steps, they look like Booleans? 100 steps, they look like Booleans? They look like Booleans for all steps. We're good. The k doesn't matter. Okay. I'll come back to do I want to come back to functions? Okay, let's do functions. When does a function, ultimately I'm doing it for this guy, right? That's the thing. But we should just do it there first. Okay, let's do it here first. When does a fold v behave like a mu alpha tau for k steps? You know that unfold fold, it eats up a step, right? If I run that, it takes up 1 step. This is a 1-step operation. These reduction steps are the steps that I'm counting. Steps of the operational semantics. Okay? This is taking 1 step. So, if I want to know if the fold v is good for k steps, then the unfold fold v needs to be good for k steps, right? But unfold fold v consumes a step, so the v only needs to be good for k minus 1 steps. Should I do that one again? Because that one's the critical one. I want to know, does fold v behave like a mu alpha tau for k steps? Right? That means that I have to be able to use it. So I have k steps right now. I draw a little timeline. I have k steps right now, and I have my fold v value. What can I do with it? I can unfold it. But as soon as I unfold it, I'm going to consume a step, and I'm going to have k minus 1 steps left. That means that if I don't write it with the unfold fold, if I just focus on the v, I can write it with the unfold fold as well, whatever, but then that would have to be the e relation. But let's just focus on the v. By the time I got my hands on the v, I ate up a step. That means that the v only needs to look like the expanded type for k minus 1 steps. Do you agree with me? Yes? Okay, that's the trick. Yes?
What if we also then continue to wrap the v and fold until we like don't have any steps?
It's okay, you're just eating them up. And now you're worried about the budget.
Yeah.
But I haven't told you what we do at top level. So hold that thought for just a second. Okay? The budget will not be a problem because you will have an arbitrary budget. But we haven't gotten there yet. Okay? Yes?
Just to confirm, is this happening, like the operational semantics, is this like the runtime or like are we looking at the size of the code?
No, not size of the code. We are literally counting number of steps at runtime. And even that, I don't want you to take it too literally. I'm using it for intuition. And then I can follow that up to say something else and say that. Let's just get there in a second. Or in a few minutes. Sorry?
Our lambda calculus doesn't have termination, right?
It does not have termination. So I'm not asking for termination, but that is okay. Here's an observation I'd like to make. Actually, let's do lambda and then I'll make the observation. So far, this is all I've given you, but I'm going to say that the problem was that the logical relation was not well founded. If my outer induction is now on the step index, then let's go back and look at this guy. Outer induction is on k, inner induction is on the taus, right? This relation, in order to define whether something looks like a good mu alpha tau for k steps, I am referring to relations that are strictly smaller. They're k minus 1. I am not referring to any k1s. So even if the type gets bigger, I have made sure that the outer induction is on the step index, right? That is going down. So the inner one can go up. It doesn't matter. Okay. I'm sort of explaining it as a math trick, but there's more to it. Anyway, let's do this, because if we don't understand this, nothing's going to work. So now what does it mean for a lambda to behave like a tau 1 arrow tau 2 if we only have k steps? All right, and here we really have to think in terms of timelines. I'm going to try to draw it here. Timeline. We are here. We have k steps, and we have in our hands a lambda. Now, if you have k steps left, you have a big program, you might do other things for a while and not apply your lambda immediately, right? For example, if I wanted to apply this particular lambda to some expression E2, I will have to take a few steps to run the E2, right? So at some point in the future, when I'm actually ready to take my lambda x colon tau 1 dot e and apply it to an actual value v, let's say at that point I have fewer steps left, and they're j. J is less than k. This is some future. Here I have k steps left. Here I have fewer steps left, j, and eventually I will have 0 steps left. Okay? So at some point in the future, when I'm actually ready to do the application, I have j steps. Maybe I'll even write that as j plus 1. Because then I'm going to use one step. Now I have j. I'm going to use the one step to do the application, which will end up substituting the v for the x and the e. Right? Sorry I don't have space up there, but I'll write down, after that one step, we have e with v for x. That is the thing that's running at j. Now I have j steps left, and I get to run the thing that I got after doing the application. And that application better be good for the remaining j. Otherwise, there's going to be a problem. Right? Okay. Now you might be thinking, when I say better be good for the remaining j, it can either keep running for more than j. It's good. It's stepping. It didn't get stuck. Or if it did terminate in these remaining j steps, then it better give me back results of the right type, values of the right type. Okay, so how am I going to say that? Here's what I'm going to say. I'm going to say lambda behaves like this function for k steps if, in the future, at some point, when I have j steps left, and you give me a value that is good for j steps, I could have written j plus 1 there, but I'm not, and I'll come back to that in just 1 second. So in the future, if you give me a value that is good for j steps, I stick that value into the body, I'm going to have an expression that is good for j steps. What does it mean for an expression to be good for j steps? Let's index that. E behaves like a tau for k steps if what? Okay. If either it keeps running past those k steps, keeps running, and it never gets to the irreducible in k, or if it does get to something irreducible in less than k, so we have to write that. So I'm going to say, for any j less than k, did I do 1 second? Okay, so for any j less than k, if, now this timeline is different. Over there I said I have k and then I have j left. Here I'm saying, suppose I take j steps. So my timeline is more like, I have, at k, I have the expression e. It runs for actual j steps, and then I have k minus j left. Okay? I'm just using them differently. Does that make sense? So for all j less than k, if I get to an e prime, and for all e prime, if e runs in j steps, so now we've consumed j of the k, right? So we have k minus j left. So if I get to something irreducible, and then I have k minus j steps, then whatever value I end up with needs to only be good for the remaining k minus j. I hope the pre-lunch hour isn't making this hard to understand. Yes?
Why can't J be equal to K?
Actually, that's why I was looking at my notes. Let me just check. I think. Trying to remember if I normally. If you, basically the intuition here is that 0 steps in the E relation, only in the E relation. If this is 0, everything looks like it behaves like a tau. And I don't even, the question is why can't I do j less than or equal to k? Okay? And basically, if this is 0, I want everything to look like it behaves like a tau. Okay? So here I'm saying that if you actually make some meaningful progress, if you, then for some number of steps that are left, you have a tau. Should really start wrapping up. Let me think about what I want to say before we stop for lunch. Okay, so I've managed to, there's one thing I do need to say. So I got lots of questions from you guys about the overall budget. And the overall budget comes into the picture here. We still want to give a meaning to E in this environment, how it behaves like a type tau. But we need to go and step index these things, right? And this is where the magic happens. At the very top level, you say, okay, pick an arbitrary k. For all k greater than or equal to 0, if you give me inputs that are good for k steps, then I will give you an expression when you plug all of that in that is good for k steps. We go and index this with k as well, but that's utterly straightforward. You just put the same k's everywhere. All of the inputs are good for k steps. So give me a whole bunch of inputs that are good for k steps. I'm going to plug them into the program, and then I should be able to run the program, and it should look good for k steps. You don't have to worry about having an overall budget because the k is arbitrary. You're picking any number whatsoever, and the thing has to work for any number whatsoever. If your number is too low, it just means you're going to keep running, and you haven't terminated yet, so there's nothing to show. If your number is really, really, really high, then most likely you ran, and as long as you're not infinitely looping, you reached a point where you had a value in your hands, and then you had to show that the value actually belongs to the appropriate value interpretation. So it works out in both cases. Either you just keep running forever past whatever the k is, and you're done, or you did terminate, you did reach something irreducible, and you actually have a proof obligation to show that whatever's left is good for the remaining number of steps. And then you have to show this for all possible k's, so you've covered everything, in a sense, right? No matter how long you wanted to run your program, because we're at the very top level, we're quantifying over all possible k's, it just works out. And then the last thing I want to say is that, since the early days of step indexing, we've been explaining this stuff in terms of this intuition of steps. But at the end of the day, you can even make decisions about which steps to count and which not. In this entire calculus that I've shown you right now, I am assuming that I'm counting application as a step, and I'm counting if then else as a step, and I'm counting every single reduction as a step. But you don't have to do that. You can set up your system and say, my problem is recursive types. I'm going to count every single reduction in the programming language as a 0-step operation, and the only one that's going to be a 1-step operation is unfold of a fold, because that's where the circularity is. Everything works out. Because at the end of the day, this is kind of a trick. It's not so connected to gas or reduction or anything. It is connected to something about observations and having, trying to stratify the relation in the limit by what observations are present. And the only place where it matters is places where the circularities are. If you count this as a 1-step and then you follow your intuition and do the appropriate reduction, right? Here, k has to turn into a k minus 1, otherwise you don't have a well-founded relation. You won't know if it's actually inhabited. So that's the one you have to solve. Okay, I'll take a couple of questions and then we quit. Yes?
I don't see where the k is used in the function arrow region.
Sorry, the k is used in the?
In the function arrow class of values.
Oh, I didn't write it there. Sorry. Okay, I never actually put this here. So lambda looks like a tau 1, a tau 2 for k steps if at some point in the future, when I have j less than or equal to k steps left, and you give me a value that is good for that remaining number of steps, then my term can run and looks like a type tau 2 for j steps. Sorry, I forgot to put the for all j less than k there. Other questions? Yes?
Why don't we need a V0 for the recursive case?
Why don't we need a V0 for the recursive case? In a sense, it is there. Because if this is 0, then you're sort of vacuously true, right? Because V can never be in -1 because -1 doesn't exist. And there is a different style of writing this. Like some years at OPLSS have written it as I define a V0 relation and then a VK plus 1 relation. There are two ways of sort of doing the math. Yes?
In the lambda case, sorry, in the function case, you just wrote for all j small equals k.
Uh-huh.
But can j be equals to k because you still have to do one extra step, right?
Yes. So here it actually does not matter. And the reason it does not matter is because ultimately there is no well-foundedness issue. Because even if this j is equal to k, our type has gotten smaller in both of these places. So that's why it's totally fine. You could do it the other way. The thing that you cannot do, the naive interpretation for function types is the following. You might say, oh, lambda is good for k steps if you give me a value that's good for k and I give you something that's good for k. That does not work. It does not work because this model, because we're now saying V behaves like a tau for k steps, V also needs to behave like the type tau for fewer steps, right? Because if it looks like it's good for up to k, then it has to be look like that type for everything less, right? That's a monotonicity property. It's a lemma we will actually have to prove in order to get all the proofs to go through, right? It's also related to the fact that these step indices are like worlds. There's something called possible worlds models. These models essentially say, they have the following kind of interpretation. Does an expression or a value look like it has this type in the current world? And usually those kinds of models, possible worlds models, always have the property that if it looks like it has, like it behaves like this type in this world, then it must look like that same type in all future worlds. So think about what I just said with respect to step indices. If it looks like it has this type for k steps, then it has to look like it has this type for fewer steps. Because in the future, I have fewer steps. Okay? We'll talk about possible worlds models and monotonicity tomorrow. All right. We should stop. Otherwise, we won't have lunch.